Okay, there we go. Uh, so in this video, I just wanted to talk about the assignment of zeros, and also the other thing I wanted to talk about was some extensions of the Hungarian algorithm. So one thing we do have to be a little bit careful about is assigning the zeros. We don't want to paint ourselves into a corner. So for example, if I had in this array assigned this last value first, and this value second, and this value third, you can see, right, that's a problem, because then I'm not able to assign the zero in this last row appropriately. Okay, so what do I do instead? A good thing to do instead is, if a row has more than one zero, skip it. If the row has exactly one zero, go ahead and assign it. And then you can go ahead and delete that row and column, because that job and that position has been filled. Okay, um, and so um, then you go through and finish all the rows, and then you go through and look at the columns. And if a column has more than one zero, you can skip it. But if it has exactly one zero, then you want to go ahead and assign that, and then close off the row and column. So let's see how that would work in this array. This first row has more than one zero, so I skip it. The second row has more than one zero, skip it. The third row has one zero, so that's been assigned, and I can go ahead and delete that column and that row. The next row has, this is the only zero, so therefore I'm going to assign it, take out this row and this column. Okay, so that just leaves this 094 and 003 left, and so when I look at the open columns here, the 094, I'm going to go ahead and take this zero out, and that takes care of this row and this column, and so that just leaves this left. And so actually it's just this zero that's left, and so I would go ahead and assign that. So this would be the last zero being assigned in that algorithm, and then that's a nice way of avoiding problems. Of course, sometimes you're going to run into some other weird issues. For example, you might have lots of zeros to choose from. And so that can be kind of a hard thing to try to do too, because you're just basically assigning things at random at that point. But of course, it's nicer to have more zeros than you need than less than fewer. But you still need to be careful, right? Because even in this case, right, even though we have more than one zero in the rows and in the columns, right? Uh, yeah, you'd still want to make sure that these two zeros are assigned, like for this zero and then this zero, or this zero and this zero, right? So you don't mess it up, and then this one would just take this sub array. Okay, so using our algorithm, there's always some kind of special case there, but so we should keep that in mind. Okay, so some more extensions. What if someone can take on more than one job? So an example of that would be if I have 3 people and 5 jobs. How would I set this up? The algorithm needs to be square, so I need to have the same number of people as jobs. So if I have 3 people and 5 jobs, then I'm going to assign some people more than one job, or you could think of it as dummy people, creating dummy people. Either way, and so we would need to create, for example, if person one can do more than one job, I would have 2 rows for that person. Otherwise, the second row would be a dummy person. Okay, and so in that way, I would create a 5 by 5. Similarly, what happens if we have fewer jobs than people? So, for example, if I have 5 people and 2 jobs, well, then you would create dummy jobs. Dummy three. In that case, you would have 3 dummy jobs, right? So that you would have 5 people and 5 jobs. Okay, so for both of these situations, we need to decide what to assign for the costs. And you would probably want to assign the dummy values last. And so one recommendation I've seen is to just use the maximum penalty or maximum cost as the cost for the assignments to the dummy variables. Okay, so in that case they would be assigned last. Okay, so what happens if some people cannot do certain jobs? Is there a way to assign costs for those? And sure, uh, replace the cost with M, a very large number. Or you could just really, I mean, when you're doing this on a computer, you would have to actually have a very large number in mind. But it kind of depends on the scale of the problem. But for us, if we're doing things by hand, we can just replace the cost by M, a very large number. Good. All right, so then some other extensions. Can we convert a transportation problem into an assignment problem? A generic transportation problem. Remember, we can assign, or we can, the very first thing we did in this discussion here was, in the last talk, was to make the assignment problem into a transportation problem. And that was nice because then the assignment problem is also easy to translate into a linear program from the transportation problem. Okay, so let's see, is it possible to convert a transportation problem into an assignment problem? So the issue is that in a transportation problem we have lots of supply and lots of demand, but in an assignment problem, what's the supply and demand? 1. Okay, so therefore if we're converting a transportation problem into an assignment problem, we're going to have to change all of our supplies and demands to 1. Let's take a look at an example for that. So here's an example where we have a supply of 2 and a supply of 3, demand of 1 and demand 4. And so this is like factory 1 and factory 2, customer 1, customer 2. Okay, so the way to deal with this, if I really wanted to convert it into an assignment problem, is for each demand, I would have to split this up. So I would have 4 columns, 1 for each of these demands. This one's already just got 1. The supply would have to be split into 2, so I would have a supply of 1 and 1 with the 3, 1, 3, 1. And the 3 here would be 1, 1, and 1, so that would be 2, 3, 2, 3, 2, 3. Okay, so putting all that together, what would we have? We would have a 5 by 5 array that looks like this. Okay, and these would be the assignment costs then. So notice that we have 5 here, 5 here, so it's still balanced. Okay, but now this is a transportation, or a, sorry, this is now an assignment problem. Good. So that's one way of doing it. What happens if we want to maximize the sum of the costs instead of minimize? So just as an example, here's some costs, and suppose we want to minimize those. Well, remember we just, we want to maximize the sum of these. So this is like profit instead of cost. So what we would do is we would negate those and then minimize the negative, because remember we're always minimizing. So here's the negative values. Now what's interesting is if I proceed as normal in my setup, right, the smallest value here in the top row is -8, then -9, -9, -7. If I pull those values out, then the array becomes like a normal array without any negatives, right? Because I'm pulling out the most negative value. And so then you just proceed as normal from there. Okay, and so that makes it easy. So the next step, of course, would be to bring down 1, 1, 0, 0. And then you can perform the rest of the algorithm as normal. Good. And so then we have some assignments there. Okay, so that's how you would perform a maximization instead of a minimization. Okay, that's it for now. These are kind of fun problems to work on. I hope you enjoy them. Talk to you later.